Hey everyone, this is Chapter 9 review. In this video, we're going to go over center of gravity, how to calculate torque, and how to solve static equilibrium problems. First, center of gravity is the average position of the weight. We can see in this picture the center of gravity is at this point. That means that there's as much weight acting on one side as there is on the other side. The object is stable if the center of gravity lies over its base of support. We can see here if we extend a line down from the center of gravity that it falls on the base of the object, which is supported by the ground there. So that means this object is stable, it's not going to tip over. But if the center of gravity was shifted over to the right, such as here, and then we extend the line down, we can see that this point here is not supported, so it would tip over if the center of gravity was shifted to the right. Let's look at an example. A meter stick balances at the 55 centimeter mark. Where is its center of gravity? When we have a uniform object, the center of gravity is going to be at the center. In this case, the center of gravity is at the 55 centimeter mark. That means that there's as much weight on one side as there is on the other, so that 55 centimeter is going to be the balance point. So it's good to think of the center of gravity as the balance point of the object. Let's look at torque. Torque is how effectively a force causes a rotation. We can see in this picture here there's an object and it's fixed at this point that we call the pivot point. If there's a force acting on it, it's going to have a tendency to cause a rotation. The torque exerted by the force is going to depend on three factors. First, the magnitude of the force. The stronger the force, the more torque. Second, the angle. If a force is diagonal, then it has a component that is perpendicular to the object and parallel to the object. The component that's perpendicular to the object is the one that's causing the rotation. The parallel component does not cause any rotation and thus does not exert any torque. So whatever force has a bigger perpendicular component will exert more torque. And finally, the distance from the pivot point to the force. The bigger that distance, the more torque. Let's look at an example. Which force exerts more torque about the pivot? If we compare forces 1 and 2, force 1 has a perpendicular component that's about this big. That is smaller than F2. So F2 is going to exert more torque than F1. And then if we look at F3, it's closer to the pivot than F2, but it's the same size. So F3 is going to exert less torque due to less distance. So F2 is going to exert the most torque. Let's see how to calculate torque. There's different equations to use, and this is what I recommend. When the force is perpendicular to the object, then use torque, tau, equals F times R. F is the force and R is the distance from the pivot to the force. Let's look at an example. Here we have a beam of length 2 meters, a force of 4 newtons. This angle of 30 degrees is not relevant to this picture. The angle here between the object and the force is 90 degrees. Because this force is perpendicular to the object, we can use torque equals F times R, just multiply the two together. Now R is this distance from the force to the pivot, so it's half of the length of the beam, which is 1 meter. So the force is 4 times 1, that's going to be 4 Newton times meter, which is the unit for torque. Now we do need to pay attention to the sign of the torque. The torque is positive for counterclockwise rotation and negative for clockwise rotation. So if you fix this point here and you see which way this force causes the object to rotate, it's going to be clockwise. That's going to be a negative torque. Make sure to put that negative. Next, when the force is diagonal, I like to use the definition torque equals F perpendicular R, where F perpendicular is the component of the force that's perpendicular to the object. Let's look at an example. Over here, the force is diagonal. So let's draw the component of this force that's perpendicular to the object. I like to draw it right here so that it's still applied at the same location as the original force. This is F perpendicular. We can see that it's opposite to the angle. It's easier to see if you draw it here. So that means that F perpendicular is F sine of theta. Now we're ready to use torque equals F perpendicular R, we're going to have F sine of theta times R. R is the whole distance from the pivot to the force. So we're going to have 4 times sine of 30 times 2. That's going to give us 6.93 Newton times meter. Once again, look at the direction of rotation. This force causes a clockwise rotation, so it's going to be negative as well. Let's look at the last case. When the object is diagonal, I prefer to use the torque equals F times D definition, where D is the perpendicular distance from the pivot to the force line. Let's see how to apply this in an example. In this example, the beam is diagonal, and the force is not diagonal. That's why we're not using the second definition. So we want to draw D on the diagram. We're going to extend the force. That's going to be our force line, also called a line of action. And then D is that perpendicular distance from the pivot to the force. So if the force is vertical, that means that D is going to be horizontal and vice versa. Now let's look at the triangle form to get this distance. This distance here is going to be adjacent to the angle, and the hypotenuse is the length of the beam. So it's going to be L cosine of theta. And actually, I put the wrong number here. This is actually going to be negative 4 newtons times meters. So let's go ahead and plug in the values here. The torque is going to be F times D. It's going to be 4 times 2 cosine of 30. And this is the one that is 6.93 Newton times meter. This torque, with the pivot over here at the bottom, is going to cause a counterclockwise rotation, which is positive. So this torque remains positive. Now let's look at static equilibrium problems. When an object is at rest, it has to satisfy these two criteria in order to be in static equilibrium. First of all, the net torque acting on the object must be 0. And second of all, the net force must be 0. So if your object is at rest and it's in static equilibrium, these conditions will be true, and it's going to help us to solve a problem. A lot of times you're going to be asked for an unknown force. So let's say we have this example here. We have a beam attached by a cable to this wall. Let's say that we're trying to find a tension in the cable. The first step is going to be to draw the free body diagram for the beam. We know that there's a tension force acting where the cable is. I'll call that F1. The beam has a weight that acts at the center of gravity, assuming it's a uniform beam. I'll call that F2. And then at the wall, there's a normal force to the left perpendicular to the surface. I'll call that F3. And then there's also a friction force, assuming there's no hinge here, that the beam is just held by friction. The beam wants to go down, so the friction is going to act upward to oppose that motion. So we have 4 forces acting on this beam. Typically, we're going to use the first equation first to solve for the unknown. We'll see this in a couple of slides. But if we look at this diagram, we can see that these conditions will apply as well. The x component of F1 is going to balance out F3, and then the y component of F1 and F4 are going to balance F2 according to the net force equations. But let's take a look at how to use the first equation, net torque is equal to 0. To use this equation, we need to be able to choose the pivot point because all torques are measured relative to a pivot point. So it's important to know that forces at or going through the pivot point do not exert torque about the pivot. We can see in this diagram, F1 is going through the pivot. If we extend it, F2 is at the pivot. These forces do not exert any torque because the distance is 0. Therefore, what we want to do when we're choosing the pivot point is we want to choose it at a location to eliminate torques that we don't have enough information about and that aren't going to help us solve our problem. For example, back to this problem, we already showed the 4 forces acting on it. let's say we are indeed solving for the tension in the cable, where would we choose the pivot point? So we don't want to choose the pivot point where the cable is, because that would eliminate the torque due to that tension force. And we want that tension force to remain in our equation so that we can solve for the unknown. We also don't want to pivot at the weight of the beam because we know the weight of the beam. So we're going to want to put the pivot point where the beam is touching the ground. That way, the torque due to the friction force and due to the normal force will be zero, and those torques will be eliminated from the equation, making it easier to solve the problem. So let's go ahead and solve the problem. Let's find the tension in the cable. And this angle here actually does not apply. And actually, sorry, I made this angle equal to 30. All right. So we know that the forces here are not exerting any torque. I went ahead and removed them to make the diagram less messy. How do we solve this problem? First, we draw the free body diagram, which we already have done, and we choose the pivot point. Next, we want to calculate any relevant variables that we need to calculate torque. F1 is actually perpendicular to the beam, so we're going to use the FR definition to find that torque. That means we need to label and define the R distance. I went ahead and redrew it here so it wouldn't be as messy. R1 is the distance from the pivot to that force F1. Because 1/4 of the length is on the left side of the force, that means that 3/4 of the length is on the right side. So R1 is equal to 3/4 L. And now let's look at F2. The object is diagonal. This force is not perpendicular to the object and it's not diagonal. So we'll use the third definition, which is FD. To use that definition, we need to draw D, the moment arm. We said that if the force is vertical, the moment arm is going to be horizontal from the pivot to the force. So let's draw it over again. We're going to have the force acting at this point. And if we extend that line down, then we're going to have D2, that moment arm, be the horizontal distance from the pivot to where that force is acting. Now D2 is a distance, so let's look at distances to define it. The hypotenuse of the triangle formed here is L/2 since the weight acted at the center. This side D2 is adjacent to the angle, so it's going to use the hypotenuse L/2 times cosine of 30. Now we are ready to set up the sum of the torques is equal to 0 equation. When we sum up the torques equal to 0, we write down a torque due to each force. We've already eliminated torques due to force 3 and 4, but we can go ahead and show that we've already eliminated those torques since those forces were at the pivot point. Now we write down the definitions. F1 R1 for torque 1, and pay attention to the signs. The F1 is going to cause a rotation clockwise. That's a negative torque. And then torque 2, that rotation is going to be counterclockwise. So that will be positive F2D2. We sum up all the torques equal to 0. Plug in what we know about each one. Well, we can go ahead and solve for F1 equals F2D2 over R1. And now plug in everything that we know. F2 is going to be the weight of the beam, which is mg. D2 is L/2 cosine 30. And then R1 is 3/4 L. We see that the L's cancel out. And now we can plug in the values. 1000 for the mass of the beam, 9.8 for G, cosine 30, and the factor of 1/2, let's not forget that right here, and then the factor of 3/4 at the bottom. All of this is going to give us 5,658 newtons. So that is how we solve static equilibrium problems. Note that in this case, we did not need to set the sum of the forces equal to 0 equation because we were able to solve for our unknown with just the sum of torques equal to 0 equation. So only use number 5 here as needed. That's all for this review video.